Hey, how we doing out there? This is 7.3 exponential and logarithmic problem solving. Now, kudos to the kid in K-Town that made this wonderful meme. Is that called meme? What is it? I don't know what these things are, but look, when you find out the next section is Mr. Bean, that is perfect. I love this so much, I'm going to make a whole video based on memes, and that's what today's all about. We're going to learn some exponential and logarithmic problem solving as well, so let's get right into that. So what do we have to know to solve these problems? Well, we have to know a couple properties of equality here, that b to the x equals b to the y only if the exponents are the same. We know that from before, so if the bases are the same and the quantities are the same, then the exponents must be the same. We're going to use that to solve some problems. Same thing with the logs. Okay, if you have a common base, then log base b of x equals log base b of y if and only if x is the same as y. So as I said, we're going to use that to solve some problems today. We're going to start number 1 right here. 16 to the 2x plus 3 equals 1/4 to the x minus 1. Now, this says solving by equating exponents. How are we going to equate those exponents? Well, we need a common base first. So I look at 16 and I look at 1/4 and I see 4 as a common base. So I'm going to rewrite this with a common base. 16 is 4 squared, and I'm going to keep that 2x plus 3 as an exponent there. And then how can we write 1/4 using an exponent on 4? That would be 4 to the negative 1. And that's 7x minus 1. Okay, so if you notice, we're getting closer to having a common base. What can I do here? Our exponent rules say I can multiply those exponents, so we're going to get 4 times. We got to be careful because this is going to be multiplying, but you have to use the distributive property. So we're going to get 4x plus 6. That's going to equal, and then when we multiply these two quantities, I'll put parentheses around that, we'll get 4 to the negative 7x plus 1. Be very careful there. Now look, we have a common base and the exponents are the same. All right, because, well, we say these quantities are equal, so the exponents must be the same. So what do we do then? Well, we can set the exponents equal to each other. So 4x plus 6 equals negative 7x plus 1. We can subtract, let's add 7x to each side. Yeah, that'll give us 11x on this side. We subtract 6 from each side. We're going to get negative 5. And then we'll get x equals negative 5/11. Hopefully you didn't get lost in my Algebra 1 skills. All right, I'm going to pause the video. Try number 2 all by yourself. Here's a hint. Use 5. Pause the video. Go! Okay, did you at least get this far here where you could write them as a power of 5? We have 5 to the negative 2 and 5 cubed. I'm going to multiply those exponents. We're going to get 5 to the 6m minus 2 equals 5 to the 3rd power. Now we can set their exponents equal to each other. So we're going to get 6m minus 2 equals 3, right? And then what do we do? Add 2 to each side. 6m is going to equal 5. M is going to equal 5/6. So that's it for the first 2. Let's go to the next type of problems. We're going to learn how to solve by taking a logarithm of each side. Now, to do this, what we need to do is first find the x. The x is in the exponent, or the variable. I shouldn't say x because here it's an n. But the x or the n, the variable is in the exponent. So we need to isolate this first. This is all by itself. Let's isolate that. So the way we can do that is by dividing by 11 in number 3, both sides. And so that will cancel on the left. We're going to get 10 to the 6x, because those 11s cancel, equals 5. Now, if we take the log of each side, this one works out nice. And we are going to get decimals here eventually, but this one does work out a little nicer. We get the log of 10 to the 6x equals, I'm just going to do this all in one step here, the log of 5. There was a 5 there. I took the log of both sides. Okay, so remember I taught you to say this, the exponent I use on 10 to get 10 to the 6x. That's going to be 6x. Okay, that's the exponent I use on 10 to get 10 to the 6x. And on the right, I got ugly number, log of 5. Now, this is a decimal. I'm just going to leave it right now, log of 5, until we can get x by itself, which we'll have to divide by 6. We're going to get x equals the log of 5/6. So we have to bring up the calculator here. So here's our trusty calculator. We have the log of 5 divided by 6. and that's going to give us 0.116495. Let's bring that down here. That's going to be what x equals. All right, so do you think you can do number 4? X equals this. I think you can. All right, pause the video. Do number 4. Go! Okay, this one's a little bit different there. Let me tell you why here. First, we need to get rid of the 7. We have to get, remember, we have to get whatever the base, we have the variable up here in the exponent. We have to get that by itself. Here, this part right here. Let's see if you're able to do this. We got to get that by itself. So let's subtract 7 from both sides. This is kind of like Algebra 1. So that's going to give us 9 times 14 to the 9n plus 8. Okay, that equals 90, right? We divide by 9. That's the coefficient in front there. So they will cancel. We're going to get 14 to the 9n plus 8. That will all equal 10. So at this point, we take the logs of both sides. Now, coincidentally, we have a 10 over here. That's going to work out nice. But on the left, it gets a little ugly. So we get the log of 14 to the 9n plus 8. That's ugly. Kind of like that sweater Bean was wearing in that one meme. Alright, so anyways, what are our rules for logarithms? Well, we can take that exponent and bring it down front, right? So let's do that. Let's bring that exponent. Let's put parentheses around it so it all looks the same here. We're going to bring that down front. So we're going to get 9n plus 8 times the log of 14. Remember, the log of 14 is just a constant. It's a number. It's a decimal. It's an ugly number. What is the exponent we use on 10 to get 10? That would be 1, so that simplifies. All right, so now what do we have to do? We have to get rid of this log of 14 thing. Let's get rid of that log of 14. So we divide both sides by the log of 14. Okay, they cancel out. What are we left with now? We get 9n plus 8 is going to equal, because they cancel, 1 over the log of 14. Now at this point, you can go into decimals if you want. I'm going to subtract 8 from each side. Okay, that would cancel out. We're going to get 9n is going to equal 1 minus the log of 14 minus 8. And then I got to divide that whole thing by 9. Now, how would we do that in the calculator? Let's set that up in the calculator right now. Okay, so we plug in 1 divided by the log of 14, and we subtract 8 from that. And from this difference here, I need to divide by 9. So that's what I'm doing right here. I'm going to n equals negative 0.7919. Let's bring that down so we can see it. Okay, so n is going to equal negative, let's write that out, negative 0.7919. It's always good to go out 4 places. That's it. So it's going to be a decimal. You go out 4 places, you'll be good enough. Okay, time for the next part. Exponentiating both sides. Okay, so to exponentiate, that means we use each side of the equation as an exponent on some base. Now, we're going to pick a smart base. Let's look at number 5 right here. First, here's basically what we got to do. We got to get rid of that natural log there. So what we're going to do, we're going to add 5 to both sides first. Okay, we're going to isolate it. Like we do in all these equations, we're going to get something equals 9. What do we get here? They cancel. So the natural log of x minus 6. Okay, so here's where we can use an exponent. This is the exponent I use on e to get x minus 6. Tell you what I'm going to use that on, e. So I'm going to use that whole side as an exponent on e. That's called exponentiating. We can do that on both sides, though, to keep it equal. Now, once we do that, if I use the exponent that I use on e to get x minus 6, if I use that as an exponent on e, sounds like double talk, we get x minus 6. Here we get some ugly number. I'm just going to leave it as e to the 9th power. We need to add 6 to both sides. So they cancel. We're going to get x equals e to the 9th plus 6, which is approximately equal to, let's pull up the calculator. Okay, here's our trusty friend Cal. We look above the natural log button here. We have e to the, and it tells you right there, we get 9th power is going to equal, oh, we need to add 6. Let's not be crazy. 8,109. And remember, we're going to go out 4 places just to keep things real. So our answer here is going to be x equals 8,109.0839. We're going to end it there. Beep. There you go. That's what x equals right there. Let's try number 6. We get 7 plus log base 2. Now this is a little different because we're using a base of 2. But let's subtract. First, we got to get that by itself because that's where the variable is. It's a log base 2 of the variable b. So let's subtract 7 from each side. So we do that, we get the log base 2 of b equals negative 10. So the exponent I use on 2 to get b is negative 10. So what I could do, I could rewrite, I mean there's a couple ways you can solve these, but what I'm going to do is, you could rewrite it as 2 to the negative 10th equals b. That's going to be a very small number. Okay, the other way you could do it is you could raise this as a power on 2. So 2 to the exponent I use on 2 to get b equals 2 to the negative 10. So these are going to cancel each other out. We get, basically on this side, we get b equals 2 to the negative 10th, or b equals 1 over 2 to the 10th. I'm just going to leave it like that. Yeah, I could figure out a decimal if I wanted to, but this way it's a little more accurate because I got all the numbers right there. I can figure it out as many places as I want to. Pause the video, try number 7. Go! Pause the video, try number 7. Okay, so hopefully you got this far. By the way, that's a real picture of Mr. Brust in high school. Don't ask me how I got it. All right, so number 7, what do? We find that this, here's the variable right here. It's inside, it's nested inside this logarithm. So we have to get that log all by itself. So we add 5 to each side, divide by negative 7. We get the log base 3 of n minus 10. Now remember, log base 3, the exponent I use on 3 to get n minus 10. So I'm going to use that as an exponent on 3. The exponent I use on 3 to get n minus 10. If I use that as an exponent on 3, I get n minus 10. And that's going to equal 3 to the first power, which is 3. So n is going to equal 13 there. Voila! How easy was that? Next question. Okay, so if you think you're good at this, go ahead and do 8 and 9. Pause the video, do 8 and 9. Then you can fast forward ahead and see if you got the right answer. Otherwise, I'm going to talk you through it. We're going to look at number 8 here. I see that the variable here is on a base of e, so that gives me a little clue of what we need to do. Let's get that by itself first. We're going to isolate that e to the negative x. So to do that, we subtract 7 from each side. We're going to cancel. We get negative 3. E to the negative x is going to equal negative 5. Now we divide each side by negative 3. That'll isolate e to the negative x, and that'll equal 5/3. I'm just going to cancel those negatives out. So we get e to the negative x. Now, I'm going to exponentiate this. I'm going to raise each side to the natural log. What? All right, so the exponent I use on e to get e to the negative x, that's just going to be negative x. And now I have, I don't know what this is. Okay, the natural log of 5 over 3, but I'm just going to leave it like that. We divide by negative 1. All right, now I can break out the calculator. This is basically the same as negative natural log of 5/3. So that's what I have in the calculator here. It's going to give us negative, what does x equal? Negative 0.5108. We'll go out 4 places, as I said before. All right, let's look at number 9. Number 9, what do we got? We got to get, again, this base by itself. Let's look at this. We're going to isolate that base. That base. I'm going to divide by 32. Divide each side by 32. Now, I can look at this, and I got a little experience here in math. Not so bad. I'm going to rewrite it like this. 1/3 x. X over 3 is the same as 1/3 x. This is all going to equal 1/16. If I reduce this, you get 1/16. Now I see a common base. What? That's why I did that. So we get 4 to the negative 1. That's 1/4, correct? 1/3 x. All right, that's the exponent. This is all going to equal, this is 4 to the negative 2 power. So a little simplification on the left, I'm going to get negative 1/3 x. We put that as a power on 4 because I multiply these two. This is all going to equal 4 to the negative 2. So this simplifies very easily into just the exponents have to be equal to each other. So I can multiply both sides by negative 3. Multiply by negative 3 over here. All right, we get 6. They cancel. X equals 6. All done. Can we check ourselves? Yes, we can, because I can go all the way back up here. 6. All right, so 6 divided by 3 is 2. I get 1/4 squared. That's going to be 1/16. All right, 32 divided by 16 is going to be 2, so that works out for us. Woo! So that's all we have to know about solving equations. So now let's apply this to some word problems. In this case, we're going to do Newton's law of cooling. Bean visits the New York Metzgerei, by the way, in German, Metzgerei is butcher, for the Saturday special grilled Brustwurst. We know that the Brustwurst is cooked to 320 degrees Fahrenheit, 325, sorry. The room temperature is 72, and when it comes off the grill, you wait 2 minutes, and then you know it's 205 degrees Fahrenheit. How long after taking the Brustwurst off the grill should Bean eat it, assuming that 120 degrees is safe? All right, so here's what we need to do. We need to look at Newton's law of cooling, which tells us the temperature at time t, and that is defined by the temperature of the surrounding environment, an initial temperature, which is the temperature of the object when it comes out of the oven or off the grill in this case, and you subtract the temperature of the surrounding environment. We have e to the negative kt. K is actually a variable that changes from, depends on what the substance is. Okay, Brustwurst has one value of K, a lead pipe would have a different value of K, water has a different value, so on and so forth. So we need to find out what that is for the Brustwurst. We do know the time, in this case they tell us it's 2 minutes. So let's sub everything into this formula right now. Okay, so we have everything plugged in here. Use different colors to be fancy. But we have the temperature at time t equals temperature surrounding environment. See how that stays the same. The initial temperature, and it's been out for 2 minutes. So we can solve this for k. That is a great thing for you to do right now. Solve this equation for k. Find out the value of k. Go! Okay, so I worked it through to this point here. You can kind of follow my work. We get 133 over 253 equals e to the negative 2k. I'm going to take the natural log of both sides here. That seems like a smart thing to do because if I take the natural log of e to the negative 2k, remember natural log is the exponent I use on e to get e to the negative 2k. That's just going to be negative 2k. And so that's going to equal the natural log of 133 over 253. We have to divide that by negative 2. So whatever that quantity is right there, we divide it by negative 2. Hopefully you get the same thing I get, k equals 0.3215. Now, here's what the calculator looks like. I'm going to show you how to store that value because we're going to need that. And I love being accurate, so I don't want to round this thing off. Watch this. If I hit this button right here between the 1 and the 4 on the left, it's called the store button. I'm going to store this into k. If you notice, the k is above the 8 there, but you have to use the alpha button. So that'll take my answer and store it into k. What does that mean? Well, if I want to use that value, it's in k. It's stored in there, just like a regular variable when you define it. All right, we're not done yet, though, because we want to know after how long, so finding a value of k doesn't really answer our question, after how long should Bean eat the Brustwurst, assuming that 120 degrees is the safe temperature. So we need to go through this whole process again. I'm going to delete all this stuff here. Let's delete it. I am going to leave the original equation though. And so what do we know right here? We want it to be 120 degrees. That's going to be the temperature, or the temperature at time t. Forgot what I was doing there for a second. So the temperature at time t is going to be 120 degrees. The surrounding temperature is still 72 degrees. We want to add to it the initial temperature. It's still coming out at 325 degrees. All right, we subtract from that the temperature of the surrounding environment. You can see what I'm doing here. If you remember, k equals 0.3215, but I have that in the calculator for later, and I'm going to say, or I'm going to solve this for t. I just heard myself say calculator later. It blew my mind. Later. All right, so pause the video, solve this equation for t. You should know how to do that now. Go! Solve it for t. Solve it for t. Okay, so I put it all in the calculator. When I'm solving this, what I got to do? Subtract 72. Did that. Divide by 325 minus 72. Did that. Take the natural log of that and divide by negative k. I forgot to put my negative before. I hope that didn't mess you up. But I found my mistake. Put that negative in. I divide by negative k, and I get an answer of 5.197. That's what you should get for t. I'm going to put that over there. Don't forget that you have K, the value K is in your calculator, but you have to make it negative. That'll find the value for T. So that's it for Newton's law of cooling. Here we get 1698 minutes. Remember, all of Newton's cooling problems are in minutes. And that's it. That's number 10. Let's go on to number 11. We're talking about the atomic bomb at Nagasaki. This ended World War II. It was the first nuclear bomb that was used in the history of mankind. This is how many joules of energy were used. What would be the magnitude of an equivalent earthquake that released that much energy? So we go to our formula sheet and we find the earthquake intensity formula, which is right here. Magnitude equals 2/3 times the log of E divided by E sub naught, which is E sub 0 is 10 to the 4.4 joules. Okay, that is the smallest reference earthquake that can be felt by man. That's just the formula. So we're basically training you here to look at a formula that's given to you. We have defined variables, decode the problem here, and be able to figure out what values go into the variables and solve. That's basically what we're doing here. All right, so number 11, magnitude. All right, so what would be the magnitude? Well, this is very simple. We don't know what the magnitude is, so we're going to just put in 2/3 times the log of, that's how much energy we have. Is it really this simple? I gave you a problem this simple. And E sub naught is always the same, 4.4. So I guess this is basically a calculator practice problem. So let's bring up that calculator, clear everything out so it looks brand spanking new here. We're going to get the magnitude equals 2/3. So if you know how to do the fractions in your calculator, you can go alpha y equals, I'm going to hit enter there, we get 2/3. If your calculator doesn't do that, by the way, you need to update it. Just giving you a heads up. Times the log. Where's my log button? Of. Now, this is 1.34 times 10 to the negative 14th. I'm going to write that as 1.34, and I'm going to use this E that's above the comma there. Remember in your calculator, E to the whatever means we're using exponential notation. That's actually scientific notation. It's 1.34 times 10 to the 14th. That's what that means. We need to divide by 10 raised, it's 10 to the 4.4 power. So we're going to raise that, something happened there, raise to the 4.4 power. Ta-da! And we need to take that and bring it down. There. A lot of extra button pushing there, but we get 6.48. That's going to be our final answer here. That's basically a plug and chug. That's too easy. Let's figure that out. Magnitude equals 6.4847 on the Richter scale. Remember I said go out 4 places. All right, last one that I'm going to do for you. I lied. It's time for you to do one. Figure out the next, I think it's the next 2. Do the next 2 by yourself. Pause the video. Go! How about that picture of Sully in his man bag? That's real. Anyways. Continuously compounded interest. Here's the formula we use. Remember, we have an amount over a certain period of time. That's going to be 8,000. We have the principal, which is how much you initially invest. Let's start writing our equation out. 8,000 equals 5,000 times E, Euler's number there, times the rate. Now, we know the rate is 9%. Please be careful. Write that as a decimal. 0.09 times the amount of time. All right, so now we can start solving this. So divide each side by 5,000. Hopefully that wasn't a problem. I'm going to get 8/5. I'm simplifying. Here's what I'm doing. They cancel. Equals E to the 0.09t. If I take the natural log of each side, so I get the natural log of 8/5 is going to equal natural log of E. They kind of cancel out 0.09t. Here's where the calculator comes in. And if you put in your calculator, the natural log of 8/5, remember that's because these zeros can't, 8,000 over 5,000 reduces to 8/5. That divided by 0.09, after we take the natural logs, that should give us 5.2223. So time is going to equal 5.2223. That's the time in years. Then you have to do like a does this make sense check, common sense check. Does that make sense? 5 years, you invest $5,000 at 9%, you'll get 8,000. Yeah, that seems reasonable. Okay, the last problem here, we have carbon-14 dating. So I go through Let's read the problem first. We have an archaeologist who discovers a site in South Carolina that contains evidence of the earliest human settlement in North America. Carbon dating of a burned plant material indicated 0.2% of the amount of carbon-14 in the sample. How old is the sample? All right, so there's our word problem. Here is our formula that we use. We have A equals A sub naught e to the negative 0.000124t. We know that we need the amount left after t years, the amount at time 0. Now, these are amounts like 12 grams and 0.1 gram, but the question gives it to us as a percent. So let's play theoretically here, 0.2%. That means what? Percent means out of 100. So that would mean that you'd have 0.2 if you started with 100. It'd be 0.2 out of 100. So the initial starting value is 100. That would be this right here. And the amount left would be 0.2. All right? Does that make sense? So 0.2 equals, we started with 100. Or theoretically, if we started with 100, we'd have 0.2 left. And this is times e to the negative 0.000124t. We can solve this equation. First thing we have to do, we have to divide each side by 100 because we have to get that e isolated so we can use a natural log. Alright, so we do that. We get 0.2 over 100 equals, they cancel there, e to the negative 0.000124t. Now we take the natural log of each side. What are we going to get there? If we take the natural log, here's a little math right there. It's all figured out for us. Take the natural log of 0.2 over 100. We divide it by, I don't want to skip too many steps, but natural log 0.2 over 100 equals natural log of e to the negative 0.000124t. The natural log, remember that's the exponent I use on e to get e to the that. Well, it's got to be that exponent. That exponent's right here. So we're going to cancel those things off. So the natural log of 0.2 over 100 is going to equal negative 0.000124 t. If I divide both sides by that decimal in front of t, I'm going to give 50117.8073. That's what equals t. So that is about, we're going to say it's about 50,000 years. Do you have to round it? No, you don't. But that's what the question is. How many years? About 50,000 years. That's how old the sample is. So you go through, you actually plug everything in, you just solve it for t. That's something that we didn't ask you to do before, and we're asking you to do that now. All right, that's it. All right, so that's it. That brings us to the Algebro Meme Challenge. We love that first meme so much, we want to challenge the rest of you to come up with your own memes and send them out. Here are the rules. Now, of course, we need some rules here because sometimes, you know those kids that don't have a boundary. We're going to set some boundaries here. First of all, these memes have to be school appropriate. If you can't say it in front of your grandmother, then don't send it out. If you wouldn't want the principal to know that you made this, don't send it out. Next one, kind of go together. Be nice and tactful. Make a meme. You can make one of the Algebros or Flip Mastery, doesn't matter. But be nice and tactful about it. We're looking for the best responses here, and tweet it out at the Algebros so we can see it. Tell you what I'm going to do. I'm going to take the best memes we get on Twitter. I'm going to throw it my next unit. We can celebrate your creativity. We'll put it like that. I love using student work. In fact, at the end of this video, I'm going to put a little video that I like to call Mr. Bean Shoots a Brick. Hey, this is Mr. Kelly Baumholder. Remember, it's nice to be important. More important to be nice. See ya!